other little thing we just have to be aware of, and we're going to move on to it a little bit more detail in a minute, is that when you add something to an aromatic ring, you change the ring's reactivity. So if you alkylate a benzene ring, so if you add an alkyl group, the product that you form is actually more reactive than what you started with. Sorry. Okay, so what I mean by that is if you add your alkyl group, okay, so you add something, let's say we've got this kind of carbocation, you would react you would lose the proton again to give you your product. Don't worry about writing out that full reaction. I'm just doing it again just to show you so you see it. This product with the alkyl group on it is more reactive than the benzene that we start with. Okay? So if your product is more reactive and you have an excess, so you have more of this reagent than you do the benzene ring, what's going to happen? Well, it's going to react with the product rather than the starting material. Okay? So what will happen is, as you move through the reaction, you will first of all create this product, but then that product so this is your product to start with. That product will react with the reagent. So we will get a reaction of one of those double bonds. And you can add a second alkyl group. Now, you might say, how do we know that it goes into that position? And the answer is, by the time we've finished the lecture today, you'll know why it goes into that position. Okay, just trust me for now. There is a reason for it. And then you can just reform the aromatic ring again. Okay, and you form a di-substituted product. Now, of course, that is going to be more reactive. This is going to be more reactive than this. And if you again have excess, you could go on and form a tri-substituted product. In this case, you don't. And again, we'll cover why later, but it's, you know, if you were going to add another product, it would be sterically very difficult because it's just too big. Again, that's just taking it a little bit further. The reaction mechanism is exactly the same. It's just to have that awareness, and we're going to look at this in much more detail. Once you've added something to your ring, you have changed the reactivity of that ring. And so recognizing that you've changed the reactivity of the ring is important. And then we'll start to see how a substituent directs the attack of a subsequent electrophile. Before we do that, though, we've got one more bit to do on this carbon-carbon bond formation. So, di-substituted product. So the last thing we're going to do on this bit is forming a Friedel-Crafts acylation. It's going to be doing the same kind of things, okay? What that means is we're going to take a benzene ring and we're going to add a carbonyl-like compound. So this is where we have, again, an sp2 hybridized at the moment in the middle of that carbonyl bond, an sp2 hybridized carbon atom. If that doesn't make any sense to you today, it will do by the time we finish tomorrow. Okay, because we're going to move on to carbonyls tomorrow. So just, if you're not sure, keep it in mind, have a look at it later. But what we can do is we can add that carbonyl group to the aromatic ring. Okay, so how do we do that? We've got our same, partners that we've seen before. We've got some kind of carbon with a leaving group attached to it, and we also have the AlCl3 that we know and love. So what happens? We have our carbonyl with its lone pair of electrons. We have the AlCl3, and we're going to do that same starting thing. We've got the halide, we've got the lone pair, we've got the AlCl3. We're going to form a bond between them, just like we've done with all the other ones. Now, this is where I get really annoyed, because I'm going to have to tell you something now that I'm then going to completely reverse when we start talking tomorrow. Okay? But it's because of the very specific things that are happening here. So what I'm going to say is we need to break the carbon-chlorine bond. Now that's a single bond. Now what I've said before is we would always break the double bond before we break the single bond. Yeah? So why aren't we breaking the carbon-oxygen double bond? The answer is, in reality, it probably would, but we're just complicating matters here. We're going to look at that tomorrow. So for now, what I'll say is, because we've got this very electrophilic chlorine now, it's got a positive charge, it wants electrons, this bond here is now incredibly polarized. The electrons in that bond will predominantly, effectively belong to the chlorine. So that bond is really weakened by it being attached to this Lewis acid. When we look at carbonyls tomorrow, I'll be telling you, you never break that bond before you break the double bond. But in this case, because of that positive charge on the chlorine, it's so polarized, it's ready to snap, just by looking at it. So what will happen is we can take those electrons to that chlorine, much like we've done with all the other ones, and what we end up with is, I'm going to draw the carbon in now just to show it's there. Okay, we're going to end up with something which looks like that. Okay, and what we can also say is why does that happen? Well, there's a resonance structure here that oxygen has got lots of lone pairs of electrons, and so it can stabilize that positive charge. So the oxygen can have the positive charge as well. Now, again, what we know about oxygen is it's more electronegative than carbon. It doesn't really want to have that positive charge. So predominantly, it would sit on the carbon. But this is just the explanation to explain why does that happen. Well, we can share that charge around. We can stabilize it using another atom. In reality, the equilibrium will lie, the resonance structure will lie with one I've circled. But we appreciate that why it's slightly more stabilized. Okay, so what do we then, so we've generated our carbocation. So we are ready to go. So then we take our aromatic ring. Okay, I'm going to draw it that way just because I want to. Okay, you don't have to. You can draw it with the carbon with the positive charge. But what I'm showing here is, again, a driving force. Look, if we react there with the carbon, that means that the oxygen can take its electrons back. Okay. And you can see that you've generated that carbonyl bond back again, that C double bond O. Again, I can still hear those little chittering away somewhere over here, that if I can hear it, the guys in front and behind you can hear it. Okay, if you want to go and chat, there's the door, I don't mind. You'll just miss all of the important stuff, fail your exams, and then, you know, we don't have to listen to it anymore, so it'll be great. So, what do we do? Well, you know, everyone's here to get a degree, aren't they? So they're not going to want to listen to what you did for, what you had for breakfast, what you did for dinner, what you're doing tomorrow night. You might be talking about this, but now's not the time to do it. Okay? Right. So we've added our carbon, and then we can lose that double bond. Okay, we can lose that hydrogen and reform our aromatic ring, just like we've done lots of times before. And I know it gets a little bit tedious seeing the same mechanism over and over and again, but that's the whole point. It is the same mechanism. So all you have to do when it comes to aromatic chemistry, learn this mechanism, understand what happens, and understand how to generate the carbocation, how to generate the electrophile. Now, the only complicating factor here, and again, get to this point, I'm happy, but I just want to show you, just because it's important that you understand that things aren't always as simple as you want them to be. When you have this kind of carbonyl, what actually then can happen is this can react with your Lewis acid. Okay. And all this means is that when, in the previous examples, the Lewis acid can be used catalytically. We can just use a little bit, because at the end of it, it gets regenerated. But when we do this kind of Friedel-Crafts acylation, we have to use a stoichiometric amount. So we have to use, you know, for however many products we want to make, we have to use one equivalence, so one molecule of the AlCl3. At the end of it, all you do is you put water in, okay, and that, basically the water takes you back to this. And the one other thing is we had the example before, and we alkylated, we made something that was more reactive. When we acylate, luckily for us, the acyl group actually deactivates the ring. It doesn't go on to do any further reaction. Okay, so same mechanism, slightly different electrophile. All I'm showing you here is important electrophiles and how they would react. And there's just that little bit of complication of how do you make the electrophiles.